This is the second lecture of the week 6 and we'll cover the joint hypothesis testing for multiple coefficients. Let's say there's a new variable called EXPN, which stands for expenditures per student. And let's say we're interested in this population regression model where we have a test score as a dependent variable and student to teacher ratio, EXPN, and percent English learner as independent variables. Let's say that we want to test a hypothesis that the school resources do not matter. So in that case, our null hypothesis will be beta 1 is equal to 0 and beta 2 is equal to 0. And our alternative hypothesis would be neither of them, or either beta 1 is not equal to 0 or beta 2 is not equal to 0. So joint hypothesis means that we're imposing a restriction on two or more coefficients. So in general, a joint hypothesis involves Q number of restrictions. So in this example, we have Q equal to 2 because there are two different restrictions on two coefficients. So we have one restriction that says beta 1 is equal to 0, and the second restriction is that beta 2 is equal to 0. So common sense idea to approach this problem is to reject the null if either of the t statistics for beta 1 or beta 2 exceeds 1.96 in absolute value. So we cannot conduct joint hypothesis testing by simply conducting hypothesis testing one coefficient at a time. And that's because if we do that, we'll be rejecting the null too often. So here, let me give you a brief reason behind why we don't do that, why we don't do hypothesis testing one at a time. So first, if we are doing a hypothesis testing one at a time, then what we need to do is to calculate t statistics for each of the coefficients. So we have this formula which we are familiar with in calculating t statistics, and when we are doing one at a time approach, then we'll reject the null if one of these t statistics, either of them or both of them in absolute value, are greater than 1.96, which is our 5% significance level critical value. So let's calculate the probability of incorrectly rejecting the null when the null is true, using this one at a time approach. Let's also suppose that the first and the second test statistics are independent. So in this case, the probability of rejecting the null is probability of test statistics of the first coefficient being greater than 1.96. and or the second test statistics needs to be greater than 1.96. But this is also equivalent to 1 minus probability of test statistics being less than 1.96. So meaning it's 1 minus the probability of not rejecting. From the second to the third line, this becomes multiplication because of our assumption that the test statistics are independent, and by definition, probability of the test statistics being less than 1.96 critical value is 0.95 or 95%. So when we plug this in, we get 9.75%, meaning that the probability of rejecting the null when null is true is 9.75%, which is much higher than 5% significance level that we want. So when we use a one at a time approach, then our rejection rate is actually greater than 5%. And actually this rejection rate under the null hypothesis depends on the correlation between the first and the second test statistics, meaning that it depends on the correlation between beta hat 1 and beta hat 2. So there are two different solutions to this problem. The first is to use a different critical value. So instead of the typical critical value that we use for 5% significance level of 1.96, we can use a different critical value, and this method is called Bonferroni method. But in practice, we rarely use this method. The second approach is to test both beta 1 and beta 2 at the same time using a different test statistics called, in this case, F statistics. Here's a formula for calculating F statistics, which includes calculation of test statistics for first coefficient as well as the test statistics for second coefficient and the correlation between the two test statistics. As similar to what we did when we conduct the hypothesis testing for one coefficient, we reject the null when this F is really large or when p-value is less than the significance level that we choose. So oftentimes we choose 5% significance level. So let's look at the formula for F statistics. F statistics is large when the test statistics for the first coefficient is large and or the test statistics for the second coefficient is large. Also, if there is a high correlation between two statistics, so in this case, if this row is large, that means that the numerator is actually small, meaning that there's overall downward pressure for the F statistics. But if rho is really large, that means that the denominator is actually small, meaning that there's an upward pressure for this F statistics. So F statistics actually corrects for the correlation between first test statistics and the second test statistics. The formula for when there are more than 2 beta is very complicated. And the good news is that we don't have to ever calculate the F statistics by hand. There is an easy command that we can use in Stata. So in Stata, we can use the command called test after running our regression command to conduct the joint hypothesis testing. So let's go back to our original example of trying to conduct a joint hypothesis testing that the population coefficient for STR is equal to 0 and the coefficient for expenditure per student is equal to 0 against the alternative hypothesis that at least one of them is non-zero. So after doing our regular regression command in Stata, we do the test of beta 1 and beta 2 being equal to 0. And this gives you the output of the F statistics as well as the p-value. So in this case, even though you don't know the critical value of 5% of F statistics, we know that the p-value is less than 0.05 or 5% significance level. So we reject the null of beta 1 equals 0 and beta 2 equals 0. And conclude that at least one of the beta is not 0.